Yeah.
Okay. Welcome to the last session before we have our free afternoon. So I hope everybody is energetic. We'll start off with Tade Kodama, who will be telling us about observational views of gaseous processes and their environmental dependence at cosmic noon. And as a Euclid person, I'm very happy with his first start.
Yes. Okay, so hello, I'm Tade Kodama from Tohoku University, Japan. I would like to thank the organizers again for hosting this beautiful meeting at the amazing location. And if the Leaning Tower ever collapses, we will be the first to be affected. In the worst case, we will be fully quenched. It's a bit scary. Okay, so I'm going to talk about the large-scale gas distribution and motions in and around the clusters and protoclusters. So I'll speak about two things. First is using the chemical evolution. Yeah, we can put a constraint on the inflow and outflow of the cold gas and its dependence on the environment. Okay? And the second, I show the tomography of the H1 gas associated to protoclusters and their surrounding structures with pair narrowband filters, targeting lime alpha and H alpha. Okay, so as we saw this diagram already in the morning from the first talk by Neil, so the theory predicts that the gas accretion process is expected to have a transition at around the cosmic noon in the halos like protoclusters or protogroups. Okay, and so before that, you have a lot of cold accretions along filaments, and so you your cluster is enshrouded by the cold gas, while the cluster potential grows with time. Those accreted gas is shock heated eventually and fully ionized to become an X-ray cluster, or it has a SD signal. And at this late stage, accretion becomes inefficient because it takes much longer time to cool the gas from that hot gas. So, and this kind of a transition is thought to be responsible for this peak of the star formation history in protoclusters. So the first acceleration and the declining afterwards. And so what kind of galaxy evolution do we expect depending on the environment? So this figure shows a cartoon, what would be happening. So in the field, inflow and outflow plus submission rate are kind of regulated and well balanced. But in the protocluster environment, as we saw in the previous diagram, you have a more efficient inflow, which end up with the cold gas rich, and therefore, you would expect the enhanced star formation rate. And also this accretion of the pristine gas may dilute the metallicity. However, as time goes on, the inflow becomes inefficient, and so you get the gas poor and suppress star formation. And also, the theory predicts the confinement of the outflow due to the ICM pressure, and so you would end up with higher metallicity. Those are the working hypotheses, okay? And so what we are trying to do is to observe those three protoclusters, at the cosmic noon, ranging from ratio 1.5 to 2.5. Okay, so this cluster is the X-ray cluster, the rich one, at the ratio 1.5, slightly after the peak. And the second cluster is the so-called spiderweb cluster, which is actually looks older for that redshift because it already has a developed red sequence. And also it shows some signal, SD signal. While the last one is a lot younger protocluster, which has clumpy and filamentary structures. And this cluster is dominated by Stockman galaxies. Okay? And those are the three targets. We measure the gaseous metallicity using near-infrared spectroscopy using VLT KMOS or KECMOS fire. And at the same time, we measure the cold gas mass with ALMA using either dust continuum or CO lines. Okay? And let me go on to the results. So first, this is a mass metallicity relation for ratio 1.5 cluster. These data points is based on stacking analysis. Using this N2 index. And this blue line shows the field. Okay, so the galaxies in cluster seems to have a slight enhancement in metallicity. Yeah. And this may be due to the confinement of the outflow that I just mentioned, predicted by DAB et al. Simulation. And, but at higher redshift, now this diagram showing two protoclusters, one older and one younger. And you see that there is a lower metallicity here, at the faint end for this younger protocluster. This might suggest dilution of the metals due to the vigorous gas accretion to this younger protocluster. And there is no such trend seen for this older protocluster, PKS 1138. And so I would argue that we are seeing the evolutionary path. So starting from this young protocluster, which show the relatively low metallicity compared to the field, and to the older protocluster, and then to the richer, the well-developed cluster. And the metallicity actually goes up with respect to the field. Yeah, that's what we're seeing here. And this actually dilution or the is consistent with the enhanced star mission activity actually seen in this particular protocluster at the faint end. So yeah, this again suggests you have more inflow going on, and which actually dilute the metallicity and also the enhanced star mission activity. Now I show this F-gas metallicity diagram, which is a key diagram to put constraints on the inflow and outflow based on the chemical evolution. And here we assume bathtub model, and we assume that the outflow rate is proportional to the star mission rate, and this factor is called mass loading factor. And in this case, the effective yield, chemical yield, gets lower by this by the factor of 1 plus lambda, the mass loading factor, which is always smaller than the original chemical yield. And so for given F-gas, if you have an outflow, metallicity actually goes down. So this is the top curve shows the case where you don't have outflow at all, right? While if you have an outflow, then metallicity goes down for fixed F-gas. That's what we see in the model. And where are the observation on the data? So the field, so the left panel shows the ratio 1.5, and the right panel shows the ratio 2 to 2.5, okay? And so the field galaxies seems to suggest a relatively large mass loading factor between 1 and 3. However, if you look at galaxies in the clusters or in protoclusters, they are higher in metallicity for given F-gas, meaning that, this mass loading factor is expected to be smaller, less than 1. Therefore, this suggests that so the lower mass loading factor due to the Asian pressure, as I said, and the gas is forced to be recycled. Now, moving on to the second topic, which is the mapping of the gas along the large-scale structures. And one way to do that is to to search for extended diffuse Lyme alpha emission using the IFU instruments like Muse on VLT or KCWI on KEC. And those works are finding spectacular, large-scale filaments seen in a diffuse Lyme alpha emission. In this case, a megaparsec scale filament, ratio 3. In this case, there are 3 filaments which intersect at the center of the group. Yeah, and so okay, yes, thank you. So this kind of filaments is evidence for filamentary gas accretion to a protocluster. But this technique is really hard because of the cosmological dimming, right? Those diffuse emission, it's really hard to detect. And therefore, we'll take a different approach, which is the dual narrowband imaging technique, targeting both Lyme alpha and H alpha. And imagine that if your galaxies are enshrouded by large-scale gas filament, like this, and then Lyme alpha photons is resonant scattered and dispersed, while the H alpha can penetrate through the cloud. Yeah, so however, if you don't have such large scale, associated gas, Lyme alpha photons can penetrate and it arrives to you, right? And therefore, using the number of the Lyme alpha emitters divided by the number of the H alpha emitters, or the flux luminosity ratio between Lyme alpha and H alpha within a certain fixed aperture, you can trace the associated H1 gas. Okay? And we apply this technique to one of the protocluster, young protocluster EM1558, and we use those two narrowband filters. One is optical, capturing the Lyme alpha, and one in the near-infrared, capturing H alpha. Okay, and this is a zoom-in view of this center of the protocluster. We see those many clamps, and the small dots show the positions of the H alpha emitters, while the larger symbols show the positions of the Lyme alpha emitters now. And those Lyme alpha emitters seems to be avoiding the densest region of the H alpha emitters. It's actually very clear. And so this might suggest that those protocluster cores may be enshrouded by H1 gas, which scatter the light from the Lyme alpha photons. And we actually applied this technique to 2 more clusters at ratio 2 and 2.5. And this is one of them, large-scale structure at ratio 2.23 in the cosmos. And again, red shows the position of the H alpha emitters, and the blue crosses show the position of Lyme alpha emitters. And as you can see, those high-density regions traced by H alpha emitters seems to be avoiding, again, the Lyme alpha emitters. And to avoid any mass dependence of the spatial distribution of the galaxies, we actually also use a mass control sample, so plotting only the limited range in mass. And we do see the same trend. So the Lyme alpha number is much less than H alpha emitters in high density regions. So all in all, so our result is kind of consistent with this global picture where the gas accretion mode has a transition at cosmic noon, from this gas-rich phase to gas-poor phase. Finally, just a brief announcement. So the ultimate Subaru project has officially started because it's fun. And this is a new system on Subaru, which has a ground layer AO system together with the wide field near-infrared instruments covering 14 by 14 Archimedes field of view. And we expect to achieve 0.2 arcsecond seeing in K-band regularly, yeah. And a unique thing of this instrument is that we have a lot of narrowband and medium band filters, which are missing in other wide field space missions. So our instrument is complementary in that sense. And so, for example, Lime alpha, H alpha, this study that I just described can be more extended with this instrument. Okay, so we are seeking for international partners. So if you have money to invest, please contact me. Yeah. So here is a summary. So I'm saying that the transition of gas accretion mode from cold mode to the hot mode at ratio 2, which leads to the transition in gas fraction, star measurement activities, and chemical evolution. Yeah, that's it. Thank you.
Thanks for the very nice talk. Regarding the mass loading factors that you are estimating using the metallicity, so I'm not interested on the relative variation between cluster and fields, but regarding the absolute value. This is based on the IMF that you assume on your calculation. Yeah. And so I'm wondering if you try to see the effect of the variation of the shift in the plane here regarding of a different IMF, because if you are producing less metals, you have a lower mass loading factor.
So to be honest, I don't believe the absolute value of the lambda from this kind of analysis, because the chemical yield still has a uncertainty, and this is a very simple model. But I mean, the difference is more important. This is a relative thing. Yeah, so I believe this difference, but not the absolute values. Okay, thanks. To be honest. Thank you.
Thank you. This is really cool. I actually also wanted to ask about this plot of the mass loading factor. So I assume what's going into the bathtub model here is that the inflow has basically zero metallicity, and that's why you need lower mass loading factor for high metallicity. So I might propose an alternative scenario related to what I was talking about this morning. If the inflow is entraining a lot of the pre-existing hot CGM gas as it flows in, that is going to be pre-enriched. So even if the intergalactic stream is basically pristine, by the time it hits the galaxy, it can have as high a metallicity as the outflow. So that might change.
Inflow actually does not change the curve very much, because if you have an inflow, actually galaxies goes down on the track, because metallicity goes down due to the dilution, and the gas fraction increases, right? And so actually the move is actually nearly along this track. So inflow does not affect much on this diagram. Yeah.
Okay, thanks.
Hi, this was really interesting. Could you go to your slide with the filaments and the clusters and the Lyman alpha emitters? I had a question there.
Which one? Sorry.
The slide with showing the H alpha emitters and the Lyman alpha emitters.
Sure. Okay, spatial distribution.
Yeah.
Okay. Right. This
one. I was wondering if you saw any difference in the numbers of Lyman alpha emitters in the filament region compared to the protocluster region.
I don't quite get what you.
Oh, okay.
Yeah. Sorry, say again?
Oh, sorry, I might have misunderstood. But did you have any filament regions identified around the protoclusters?
Okay. So the photometric study of the more general galaxies, like starring galaxies, using, for example, BZK selection. That's exactly what we are working on at the moment.
Okay.
So I cannot show you right now. But
thanks.
Yeah. So the next talk is by Bugiani. We'll be talking about investigating ionized
quiescent galaxies at cosmic noon with JWST. Letizia.
Yes. Oh, this works like this? Okay. Hi. Hello, everyone. I'm Letizia Bugiani. I'm a PhD student at the University of Bologna. And today I would like to discuss ionized gas in quiescent galaxies at cosmic noon, and what we found investigating this kind of strange combination with JWST. This work is part of the Blue Jay collaboration, so all of these people contributed to my work. So, yeah, I will go like this. Okay, great. So, why do we care about ionized gas in quiescent galaxy? Well, I am actually more interested in the quenching of star formation in galaxies and how a galaxy transitions from star forming to quiescent. This is a gas conference, and so we all know that the gas cycle is crucial in order to understand star formation in a galaxy, but it is also crucial in order to understand how star formation is halted in a galaxy and a galaxy becomes quiescent. So this is why we ought to study gas in massive quiescent galaxies. And why do we need to study quenching? Well, for example, for many reasons, but for example, we know that there is a discrepancy between the dark matter halo distribution and the stellar mass function in galaxies. And at low masses, we think that this is maybe due to feedback from star formation. At high masses, it may be due mostly to feedback from AGN, or maybe due to consequence of gas-rich mergers. And this has been implemented in many simulations, but the observational proof of this mechanism at work is still kind of elusive to see. So this is why we selected a sample of quiescent galaxies from the Blue Jay survey catalog. This is Cycle 1 JWST observational program that targeted 151 galaxies at cosmic noon in the cosmos field, obtaining both near-spec MOS observation and parallel NIRCam observations. And here you can see one of the spectra of a quiescent galaxy. I think it's very beautiful. You can really see the absorption lines clearly, from which we can get constraints on the stellar continuum. But we can also see some absorption lines from neutral gas, which have been studied by Dr. Rebecca Davis. And what interests me is that we actually can see some emission lines from ionized gas. First, in order to isolate the emission due to ionized gas, we need to first subtract the stellar continuum. So the stellar continuum is fitted using a prospector that is fitted both to the photometric and the spectroscopic data, and this work has been done by Minjung Park. She's a PhD student at Harvard, and her new paper is recently out on the archive. We selected a sample of 16 quiescent galaxies by taking galaxies with a star formation rate that is below 1 dex, the star formation main sequence at this redshift. This is the results of the single Gaussian profiles fitting of the emission lines in some of the galaxies. And in blue we have the data, the continuum subtracted data, and in red we have the fits. And as you can see, the first surprise is there are actually many emission lines in these galaxies. And actually only 3 galaxies of 16 do not show any emission lines, which means that there is a widespread presence of warm ionized gas in this, I remind you, sample of massive quiescent galaxies. In fact, we are able to construct the emission line diagrams for this sample. The quiescent sample is in the magenta points, and as you can see in the BPT diagram on the left, most of the galaxies are actually found in the AGN-powered side of the diagram. And this is also the case in two other diagnostic diagrams. So this means that there is actually hidden AGNs in this population of quiescent galaxies, and this can also be seen using another diagram. This is the one diagram, for example. These AGN are not seen in any other bands. They are not detected in X-ray, and we only find one radio detection. But if we take the optical selection as true, we find that actually there are 50% of hidden AGNs in this population of galaxies. And this is really, I think, due to the quality of the JWST data. For example, we have this study from 2019 that uses a very similar sample of quiescent galaxies at redshift 2 with CACMOS fire data, and you can see the comparison between the stack of 18 galaxies and just one of the lowest signal-to-noise ratio in my sample. So you actually really need JWST to see these things. Of course, we check that they are actually quiescent galaxies, so we get the star formation rate using the H-alpha line luminosity, and they are actually quiescent galaxies. And not only that, but in a subset of 4 galaxies, we actually can fit a double Gaussian profile to the ionized gas emission lines. In the first column, you can see the single Gaussian profile fits, and in the second column, we added a broad and shifted component. And as you can see, there are ionized gas outflows in these galaxies. And by the studies of Rebecca Davis on the neutral sodium deabsorption lines, we also find that all of these galaxies have neutral gas outflows. The most egregious case is Cosmos 11142. This galaxy has exceptionally powerful outflows, and you can read the article only on these galaxies by my supervisor, Ciribelli. And for this galaxy, we were able to get the mass outflow rate both from the ionized phase and the neutral phase, and compare it to the star formation history of the galaxy plotted in red. And as you can see, from the ionized gas phase, we do not have actually that much mass leaving the galaxy. But if we pass to the neutral phase, then the two quantities are comparable. So we can actually explain the quenching of this galaxy by AGN-induced outflows. Lastly, this is the final part of the work that I hope to publish in the next week or the next on the archive, so look out for that. I looked at the AGNs that are in my sample, and they are generally with low volumetric luminosity and low Eddington ratio values. So we hypothesize that the star formation quenching and the maintenance of low star formation rate in these massive galaxies is mostly due to low luminosity AGN feedback. So I leave you here with my main conclusions, and I'm happy to take any questions. Thank you.
Hi, Letizia. You said that the double Gaussian profile is related to outflow, but how can you ensure that instead you're not looking at a binary AGN? So the second Gaussian component is the broadline region of a second supermassive black hole?
It was a surprise at all to find that there is an AGN, like an active supermassive black hole inside of this galaxy at all. I don't know if we have the resolution to do that kind of thing, also because we have a deep spectra, but the resolution in the wavelength is not that high. So, of course, it may be like that, but you know, I think this is the easier answer.
Thanks, Letizia, for the nice talk. If you go back to one of your previous, the first slides, where you show the imaging with the slit of JWST. I'm wondering if all your galaxies, okay, so in your case, your spectrum is not coming from all the galaxies, but it's just a part of the galaxy, right?
Yes.
So how you can be sure that it's just a Gaussian? If there is like a, I don't know, for observed like a rotating disk, you are just taking a part of the galaxy. We already know that it's not a Gaussian probably.
Yes, of course, that's like a problem. And in one of the galaxies that we have, we actually have we have found that we had a wrong flux calibration because the slit only took the bulge and there was actually a disk around it. But we got strange values with the estimation of the volumetric luminosity from the three lines and things like that. So for this, they are quests and galaxies. They are ellipticals. They do not show any sign of disks. So we only do flux calibration, and then we hope that the emission lines may be even more how do you say overestimated. So yeah, that is a thing to take into consideration. Yeah, thank you.
Very briefly, when you show the main sequence, you said that you obtained the star formation rate from H alpha. I was wondering, and then you have arrows pointing down. I was wondering instead if you have absorption, the star formation rate may be underestimated. So why do you have?
Oh yeah, those are actually the AGNs. So they are arrows pointing down because we know that from the line ratios there are AGNs. So most, we hypothesize that most of the H alpha is coming from the nucleus and not from star formation rates. So that's why they are upper limits. Yep.
No, two. So besides the very nice lines that you have shown, do you have any other detection, for example, O1, to build up alternative diagnostic diagrams?
I have looked for one, but it is not detected in most of the galaxies. So, like, I have a diagram for that as well, but they are all like upper limits. So, I think just 3 are okay. I also looked at some.
Is that compatible with the flux that you would expect for an AGN?
I have not looked into that. But in general, the fluxes of this line are low, even though like these are not very powerful AGNs.
Okay, I think we need to finish here, so let's thank Letizia again. And the next talk is going to be by Noah Rogers. So, Noah will tell us about the chemical enrichment of redshift 2 to 3 galaxies with Cecilia, or Cecilia, not sure.
Okay, cool. All right, thank you. Hello, everyone. My name is Noah Rogers. I'm a first-year postdoc at Sierra at Northwestern University. Today, I'm very excited to talk a little bit about the chemical abundance patterns that we observe in star-forming galaxies at cosmic noon observed with the Cecilia program. So a theme that has come up a couple of times this week is the importance of measuring the chemical composition of the gas in a star-forming galaxy, which is a direct tracer of the star formation that has taken place within that galaxy and different galactic evolutionary mechanisms. This is perhaps most easily seen in the relation between the overall chemical enrichment of a galaxy, traced by the oxygen abundance in the ISM, and the total stellar mass of the galaxy, or the mass metallicity relation, which is shown here on the left. And this can be understood as successive generations of star formations going off and enriching the ISM with the products of stellar nucleosynthesis, and the shape of the MZR can be affected by other galactic evolutionary mechanisms such as metal-rich outflows driven by supernova feedback or the infall of pristine metal-poor gas. And while it's obviously important to measure this total chemical composition, there's much utility in measuring the relative chemical abundances of other elements. So an example of this is the relative nitrogen to oxygen abundance ratio in the ISM, which is sensitive to the enrichment from different stars. So here on the right, we're plotting this relative nitrogen to oxygen abundance ratio against the oxygen abundance in the gas measured in metal-rich H2 regions, which are the colored diamonds, and low metallicity local galaxies, which are these gray circles. Now at the low metallicity end, the NO ratio is relatively constant and plateaus. This is metallicity independent. This is a metallicity independent abundance ratio from enrichment from massive stars or metal poor intermediate mass stars. But as the ISM progressively gets enriched with more oxygen abundance, metal-rich AGB stars release additional nitrogen into the ISM, resulting in an enhanced N-to abundance ratio. So measuring these two abundance ratios allows us to essentially test if these metal-rich intermediate mass stars have had time to enrich the ISM. And we can play a similar game with other elements. So for example, other common elements that we can measure from an optical spectrum of a star-forming galaxy include neon, sulfur, and argon. When we plot these abundance ratios relative to oxygen in the local universe, again, these are all from SDSS, we see that these abundance ratios are relatively constant, show no trend with metallicity or ionization, and are pretty consistent with the solar abundance ratios, which are plotted as these horizontal orange dashed lines. And what this is telling us is that all of these elements have a very similar nucleosynthetic origin and are released to the ISM on similar timescales. For these elements, these are the alpha process elements produced in massive stars and released via core collapse supernovae. So this is great. We can use these chemical abundance ratios to not only understand these different enrichment mechanisms, but also the timescale of release to the ISM. But how do we actually measure the gas phase abundances in the ISM of a star-forming galaxy? Well, if you observe a typical star-forming galaxy in the optical or near-infrared, what you'll find is an emission line spectrum, and this spectrum is rich with information concerning the ionization state, the physical conditions, and the chemical composition of the gas. And in particular, if you can measure very faint, temperature-sensitive auroral lines, and when I say very faint, this is something like 1% the flux of H beta, you can directly calculate the electron gas temperature, use that temperature along with the emission line emissivities, and calculate the ionic abundances you're interested in. This is the direct abundance method, and the most robust direct abundances can be measured when you have multiple direct electron temperatures. So if we make the very simplistic assumption of the ionized gas being composed of this kind of onion shell structure of ionization zones, we would like an electron temperature in each ionization zone for reliable ionic abundances, because the gas that contains high ionization species, say O++, is not necessarily coincident with the gas containing low ionization species like O+, N+, N+, and S+. And from the local universe, we know that the electron temperatures in these different ionization zones are indeed related to one another. These are the electron temperature scaling relations, or TT relations. What's being plotted here in each case is the intermediate ionization zone temperature, as measured by sulfur 3, against the low ionization zone temperature and the high ionization zone temperature. And what we can see is that not only are these temperatures correlated with one another, but there's very low scatter about these electron temperature scaling relations. So in the case where we're missing a direct electron temperature, we can use a measured temperature and one of these temperature scaling relations to infer the electron temperature in a different ionization zone to calculate the ionic abundances within that zone. Great, so this has been an overview of kind of the direct abundance method as applied at redshift 0. So what was the state of high redshift direct abundances pre-JWST? Well, from large ground-based surveys like KBSS or MOSDEF, we know the general emission line trends of high redshift star-forming galaxies. These galaxies show strong collisionally excited lines from metal ions that result in offsets from typical line ratio diagrams such as the O32R23 diagram or the traditional BPT. And all of these offsets can be explained by these galaxies having an on average harder ionizing spectrum at fixed gas phase metallicity. But that's the challenge. Actually measuring that gas phase metallicity is very difficult, and despite Herculean efforts from the ground, before launch of JWST, only 25 galaxies had direct oxygen abundance measurements, and the abundances of most other elements were totally unconstrained. And furthermore, no high redshift galaxy had more than one direct electron temperature, so by default, they had to use the electron temperature scaling relations, which may not necessarily have the same functional form at high redshift, especially so if these galaxies have, on average, harder ionizing spectra. Now, obviously, the prospects have changed greatly with the launch of JWST. This is one of the early release science spectra showing the intense collisionally excited line, the temperature-sensitive line of oxygen 34363, but also the collisionally excited lines of other metal ions such as neon-3. And this led to a flurry of results not only characterizing the oxygen abundance, but also the relative neon to oxygen abundance at high redshift. But spectra like these still leave a couple of open questions. First, what are the electron temperature trends from other ions, and how do these physical conditions of the ISM evolve with redshift? And what are the abundance patterns of other elements beyond oxygen, particularly at cosmic noon? So there are many JWST Go programs that are capable of addressing these individual questions. I'm going to talk about the initial results from just one of them. This is the Cecilia program, co-PI'd by Alison Strom and Gwen Rudy. Cecilia targeted rest UV color-selected star-forming galaxies at cosmic noon in one field of the Keck baryonic structure survey. These galaxies generally have very deep archival spectra that cover the rest frame UV and optical. An example of one of the Cecilia galaxies is shown here on the right. This is a Mossfire spectrum showing the strong optical collisionally excited lines from metal ions and hydrogen-1 recombination lines, but is missing the necessary temperature-sensitive lines to actually calculate the abundances of the elements. So to obtain these faint temperature-sensitive emission lines, we obtained deep 30-hour G235M spectra, and then shallow G395M spectra to cover some of the rest to near-infrared strong lines. So this program has been fully executed. We have 23 galaxies between a redshift of about 2 and 3, and I'll point you to Strom 2023 for a composite look at the spectrum, but just to highlight one galaxy, this is the typical Cecilia galaxy spectrum. This is a galaxy at redshift 2.3. This looks like a redshift 0 star-forming galaxy. Like, we have all of the strong lines we'd want. We have the near-infrared sulfur-3 lines, the Paschen sequence at high signal-to-noise, and, if you squint closely, temperature-sensitive auroral lines. 20 galaxies in the sample have the sulfur-2 strong lines. This is a density-sensitive doublet, and so we can directly calculate the electron density in the ISM at cosmic noon. And consistent with ground-based surveys, we find that on average, the Cecilia galaxies show slightly higher electron densities when compared to local star-forming galaxies from, say, SDSS, although there's a tail to lower electron densities that's more consistent with local star-forming galaxies. We have 17 galaxies with the O2 auroral line detection. This characterizes the temperature of the low ionization zone. For example, shown here in the bottom left. We have 10 galaxies with sulfur-3 auroral line detections. Again, this characterizes the intermediate ionization zone. And if you're squinting closely at these names, we have some repeaters. So we'll be able to populate the intermediate to low ionization zone electron temperature scaling relation to calibrate for application at cosmic noon. Okay, so this has been a high-level overview of the survey, and so I'd like to focus just on one galaxy in this sample in particular. So most galaxies are observed below a redshift of 3, but at about a redshift of 3, the oxygen 3 auroral line redshifts into the very deep G235M data. So one galaxy, D40, is at a spectroscopic redshift of about 2.96. This is the near-spec spectrum of D40. It shows, again, the strong collisionally excited lines of oxygen 3, in the near-infrared, the sulfur-3 nebular lines, along with helium-1, 10-830. But if you really focus on the G235M spectrum, we see high signal-to-noise detections of the oxygen 3, sulfur-3, and O2 temperature-sensitive emission lines, along with the strong lines of many other metal ions present in the ISM. So we can compare the electron temperature trends, the simultaneous electron temperature trends measured in D40 to local temperature trends. So the green circle are the direct temperatures measured in D40. The gray diamonds are local metal-rich H2 regions. Blue squares, low metallicity local galaxies. The solid blue line is the empirical electron temperature scaling relation to the H2 regions. The red solid line is a photoionization model TT relation. So what we see is that the sulfur 3 and O3 temperatures in D40 agree very well with the local empirical direct temperatures and with the electron temperature scaling relation calibrated on local ionized regions. However, this is just one data point, and for Cecilia, this is the only galaxy where we have an oxygen 3 temperature, but other JWST programs will be able to populate this diagnostic diagram and calibrate a new electron temperature scaling relation for application at high redshift. But using our directly measured temperatures, we can calculate the direct abundances of D40 from the near spec data alone. And this is the nitrogen to oxygen versus oxygen abundance diagram for, again, these high metallicity H2 regions, low metallicity galaxies, and D40. Here, the open blue squares are low metallicity galaxies that are missing a direct measurement of the intermediate ionization zone temperature. And what we see is that the NTO relative abundance in D40 agrees very well with the primary plateau established in the local universe. This is to say that D40 has been enriched by massive stars and primarily metal poor intermediate mass stars, such that we don't see this increasing secondary enrichment of nitrogen. But we can also measure the sulfur and argon abundances in D40, and when we do and compare these to the abundance trends in the local universe, they are significantly subsolar. So there's a large scatter in the sulfur to oxygen abundance ratio in the local universe. This is related to the observational challenges associated with measuring the sulfur 3 lines in the near infrared, but these challenges do not apply for the argon lines. And indeed, in the local universe, there's a tight clustering around the solar abundance ratio, yet D40 is 2 sigma away from the solar abundance ratio. Furthermore, we can use the upper limits on other emission lines from argon, tracing a more higher ionization states of argon, and even this upper limit is significantly subsolar. So what are these abundance patterns telling us? Well, modern nucleosynthesis models indicate that both sulfur and argon have a non-negligible type 1a supernova contribution, such that the sulfur to O and argon to O abundance ratios in the ISM may be sensitive to the star formation histories. And considering that the age of the universe at D40's redshift is only 2 gigayears old, this galaxy may not have had sufficient time to have a large number of type 1a supernova go off to release this additional sulfur and argon into the ISM. However, I should note that the relative yields of sulfur and argon in both core collapse supernovae and type 1a is relatively constant. So this abundance ratio, sulfur to argon, is not sensitive to the star formation history of a galaxy. And indeed, what we find is that the sulfur to argon abundance ratio in D40 agrees with the solar value. So again, this might be arguing that D40 has been predominantly enriched by core collapse supernovae. But if I want to leave you with one takeaway, it's that we can now measure these abundances from different elements in the ISM of high redshift star-forming galaxies. This is just one galaxy in the Cecilia survey. There are more results to come. Thank you for your attention. I'd be happy to take any questions.
Very much, Noah.
Thanks, very nice. Can you tell us how good or how bad are the standard models then to determine metallicity with respect to this sophisticated measurement?
Well, I think that's one of the forthcoming goals of cycle 1 and 2 programs is to recalibrate these strong line calibrators, because the problem with using these local relations is that if the galaxies at cosmic noon are described by harder ionizing spectra, the calibrations, the empirical calibrations that we have for the strong lines in the local universe will not work. So we are working to measure these direct abundances at high redshift so we can empirically calibrate these new strong line relations for application at higher redshift. But that's a work in progress, and we will need more statistics than just the Cecilia survey to really fully calibrate these data.
Thanks, Noah. Good talk. Can you say something about the ionization of D40 in comparison to your local universe dwarfs? Is it similar, or is it more highly ionized?
So let's see. So I'm trying to remember the ionic abundance ratios off the top of my head, which is, let's see. So if I remember, the sulfur abundance, so the sulfur double plus to sulfur plus abundance is consistent with the local dwarfs. but I don't remember the oxygen abundance ratio off the top of my head. I would have to check. For the O3-2 ratio itself, which is kind of the direct tracer, we don't have the O2 nebular lines from the NIRSpec data alone. It's a comparison of the O2 aurora lines. So I don't want to quote that ratio because that's a little more subtle and challenging.
Yeah, as a follow-up, does helium-2 4686 fall in, and do you detect it very often?
Yes, for D40, we have like just at the 3 sigma level, I would not put a lot of stock in it. It is narrow, so it's not indicative of like a Wolf-Rayet feature. I will say though, the argon 4 lines, which are also similarly very high ionization, we just have an upper limit. And that's actually what's producing this upper limit in the argon to oxygen abundance ratio.
I'll use my, so just one comment, which is that at low metallicity, we don't know that Wolf-Rayet stars have broad helium too, so that's a question. But I was curious about what do you assume, because for several of those lines, you don't see all the relevant ionization stages. So what do you use for the ionization correction factors in this?
Right. That is another major challenge for all high redshift, well, all local abundance surveys and high redshift, is that we are missing ionization states for many of these elements. So for oxygen, it's very easy. Just measure O+, O++, call it good. For argon, the only missing ionization state is argon plus. And we have an upper limit on argon triple plus. We have a direct measurement of argon double plus. So for argon in particular, the ICF doesn't show much change because you're considering a potentially large fraction of very low ionization gas, which is not what D40 is. The ionization state of D40 is not consistent with that. For sulfur, we could be missing a significant fraction of sulfur triple plus. And there's no way around that. Another goal is to try to calibrate new photoionization model ICFs for application at high redshift.
Great, thanks. Okay, I don't see any further questions. Oh, there's one last question back here.
Hey, thank you. Did you compare these abundances to damped Lyman alpha systems measurements, for instance?
I have not done that yet, but something we could do with the full sample, absolutely, yes.
Because they have exactly the same lines in an absorption, so it would be very nice to do the comparison.
Yeah, absolutely, yeah. Any additional abundances to compare at high redshift to try to interpret these abundance patterns would be greatly helpful. So.
Thank you.
Of the session is Alessandro Marconi. He will talk about accurate metallicities of the ionized gas with a new approach to photoionization models. And afterwards you'll have a cage fight with Noah. Alessandro, stage is yours.
Thank you. Thank you, Readle. First of all, let me start by thanking the organizers for allowing me to present this work. I sincerely apologize to all of you because I'm present only today, but it's the curse of living too close to the conference and then having urgent matters coming in, and you are not across the ocean, so they can't bother you. Anyway, so let me also acknowledge the large group of collaborators, most of which are in Florence, and some of them are here in the audience. So I want to thank, first of all, Noah for the wonderful introduction earlier, so I can skip briefly a couple of slides. I don't have to tell you why it's important to measure metallicity in the ionized gas in particular, because we want to constrain the evolution of galaxies, scaling relation and so on, especially their redshift evolution. But I can just remind you that, as Noah mentioned, there is one way to measure the metallicity of the ionized gas with the so-called direct method, the empirical method, the T method, which is based on the ratio between the auroral lines and other strong lines. This is what Noah presented, but there is also a way to measure this metallicity with photoionization models. And both methods can be used to calibrate the so-called strong line method, which basically is the relations between ratio of strong lines that you detect even at the lowest signal-to-noise spectra with metallicity. And that's the problem that mostly is related to the work by Noah and the work I will present, is that verify whether the strong line method is valid also at high redshift, or if there are evolutions in the physical properties of galaxies. So there is the first problem, that if you compare the metallicities measured with the T method, the so-called direct metallicity, and the photoionization model, there are discrepancies, which results, as shown in this example, in two different scaling relations. So where is the problem? Well, let's see what the photoionization models are doing. Basically, we have been using photoionization models for 40 or more years. These photoionization models are pretty successful in reproducing the global galaxy properties. However, if you look carefully, they still struggle with the single object, reproducing the single objects. And most of all, the problem is to reproduce line ratios from different excitation levels, from ions of different excitations. But probably one of the reasons why this is so is because when we are trying to model the spectrum of the galaxy, the photoionization models are not able to reproduce the complexity which goes into a single spectrum of a galaxy. It's a combination of hundreds of H2 regions, and even the single H2 region is a combination of very gas filaments, condensations, and so on. So how can we account for this complexity? So first of all, let's start from a consideration. The line luminosity is an integrated quantity. This means that if we want to reproduce an emission line luminosity, we don't really need the exact distribution, spatial distribution of gas. But we just need to have the correct volume which is emitting a given ion, the correct density and temperature, and that we get the line luminosity. So if we don't know the real distribution of the gas in the galaxy, we can simply try to reproduce it with a combination of simple so-called single cloud models that you can compute with simple geometries. And the combining factor, the weights which combine this model, can be selected just to provide the best match with the observation. So the assumption here is that if you have many emission lines and your model is able to reproduce them, then you probably have the right combination distribution of physical properties of ionized gas, even if you don't really know the exact spatial distribution. So this is what we came up with the home run, highly optimized multi-cloud emission line ratios using photoionization. I spent half a morning with ChatGPT to find an acronym that I didn't like, but it worked for me. So let's start with an example of a model fit to explain how home run works. So we start with the spectra of an H2 region, simplest thing that we can get, and we use cloudy with the standard prescription, standard input parameters, and then we consider all these emission lines which we try to reproduce at the same time. And in particular, I would like to mention that 5 of these are the so-called auroral lines, which are important even for the photoionization model, not only for the direct method. So we compute a grid of single cloud photoionization model, a grid for a given ionizing continuum and a given metallicity. This grid is an ionization parameter and density. We select the models with the proper weights which can reproduce the observed spectrum. So we select the best weights, and usually when you have 100 models, only 3, 4, 5 have weights which are different from 0. If you know what I'm talking about, just think about PPXF with the stellar templates. This is the same with the emission line templates. And then you compute a sort of a chi-square. You compute a sort of a chi-square. This is a reduced chi-square. And you repeat varying the oxygen metallicity. And you find a chi-square curve. And usually it has a very, very deep minimum. And this gives you the best model and the abundance of your model. Here is an example of a model fit on a real H2 region. As you can see, this is plotting the ratio between the model prediction and the observed. The gray area is a plus or minus 10% discrepancy. And as you can see, all these emission lines are reproduced at the same time with an error which is less than 10%, which are really dealing with the accuracy of the atomic parameters here. And the other thing I want to point out is that the chi-square is so deep that you need a logarithmic scale to plot it and to see something, and this is telling you that this method is not degenerate. Another thing, these are the models which have weights different from 0. You can, of course, compute average ionization parameter and densities. So here is an example of the application of this model to a sample of H2 regions. We have selected those 22 H2 regions with very high signal-to-noise ratios from the Chaos project. And as you can see from the value of the reduced chi-square, all the models basically have a reduced chi-square less than 1, which means that on average all the lines are reproduced to better than 10%, which is the assumed accuracy that we consider for the emission lines. And here you can see line-by-line comparison and model and observation, and the red lines are the plus or minus 10% discrepancy. So these models basically are able to reproduce 18 emission lines at the same time, which in accuracy, which is more or less better than 10%. But most of all, you can notice that we can easily reproduce at the same time oxygen 1, oxygen 2, oxygen 3, sulfur 2, and sulfur 3. So what can we learn from this? First of all, let's take the emission lines predicted by the models and let's apply the direct T methods to the lines predicted by the models. And you see that if we compare those with the abundances computed with the observed line, there is quite a good agreement. This is just another way to say that our model basically reproduced the emission lines. But we can do something else. Let's take the best models, which are the red ones, and the green one are the models which are basically consistent within a small variation of the chi-square, and let's compute the metallicities applying the TE method. And then let's compare with the real metallicities of the model. This is just a comparison of the TE method applied to the model and the real metallicity of the models. Unfortunately, the blue line is the one-to-one line, which is showing you that the direct T method is able to reproduce the metallicity of the model, but with an error of about 0.1 dec. But this error can even be much worse, even by a factor 10 or more. So this is something which has already been found in the past. It's not nothing new, but we just confirm and we caution about the T method here. Now, this method can be used to recalibrate the strong line method in local galaxies, can be used to measure the variation of the abundances in nitrogen and sulfur as a function of oxygen abundances, confirming the standard relation. But we can also apply it to JWST, of course, data. And we have this program, which is called MARTA, Measuring Abundances at High Redshift with the TE approach, which is a program similar to the one that Noah just showed. Basically, we are observing about 100 galaxies in cosmos with a very deep signal with very high signal to noise. And the idea is to detect these infamous auroral lines. And this is an example of a spectrum. Maybe you can see this one. And basically, if you think, it's quite impressive that the spectrum of a redshift 2 galaxies has a signal to noise better than many spectra of the SDSS. Anyway, these are the results of applying this model. We find a metallicity, for instance, in this galaxy, which is larger than the one of the TE method, even if we are reproducing all of the lines, and this is where, for instance, the home run metallicity goes. Now, I have a little time, just quickly I will show this is the first relation between the oxygen 3 and oxygen 2 emission lines. These are the yellow stars for 7 galaxies, which they do follow the relation, the one-to-one relation, which apparently is what we observe locally. Now, applying these models to other high redshift galaxies, which have been available from the literature, what we find, for instance, if we look at the average ionization parameters and the metallicities, that these high redshift galaxies has a distribution of average ionization parameters which are similar to the local galaxies. But if we look at the average densities, you see that a significant fraction of these galaxies have a very high density, a factor of 10 to 100 larger than what you observe locally, which is, after all, something that we expect to happen at high redshift. But this could affect also the TE metallicities, the direct metallicity. I want to conclude I couldn't resist because I wanted to show briefly application of this method to active galactic nuclei, but before of this, since there are also talks about outflow, I want to show these results that my PhD student Cosimo Marconi is obtaining by applying our kinematical tool, MoCA 3D. Basically, this tool is a kinematical fitting tool which allows to correct for the complexities due to the clumpiness of the emitting gas. This is, for instance, a galaxy, famous galaxy, NGC 1365. These are Muse observations, flux, velocity, velocity dispersion, very complex maps, probably consistent with a radial ionized outflow. And this is what this model is able to do. This is just telling us that this outflow in these galaxies is just a conical radial outflow with nothing particular, and all the complexity is due to the clumpiness of the emission. This works in many other galaxies with very different maps, morphologies, but all of these just radial outflows. Now, we can measure the velocity as a function of radius. We take all these galaxies and we plot the velocity as a function of radius after, of course, rescaling for projection and for the different distances. And the result that we get is this one, after we normalize to the central velocities. Basically, all these galaxies, which have very different appearance, they do share this behavior, constant velocity, and after 1 kiloparsec, roughly, rapid acceleration of the outflow. And this is basically consistent with the prediction from Andrew King's and Kastiti Zubov model. Basically, here we are seeing the terminal velocity of the momentum-driven phase of the outflow. Then after 1 kiloparsec, which is where more or less the inverse Compton cooling becomes ineffective, you have the rapid acceleration due to the energy-driven phase. So, but the point is that we can measure the velocity, we could measure also the mass outflow rate. And this is, for example, what we get in Circinus. There is a peak of mass outflow rate, and the problem is this peak of mass outflow rate due to our very simplified assumption in estimating the gas of the mass of the gas, or is this due to a physical, or is it real? Because if it's real, and we observe many of these peaks, we can constrain the burstiness of this outflow, getting time scales of about 10 to the 6 year, which is very, very interesting. So how can we measure the mass of the outflow? By applying home run. For instance, this is an example of an application to this aperture. This is the mass that we get as a function of the H-alpha luminosity, average density. This is the formula which is usually assumed in the literature or something similar. We have the problem that we don't know the density. It's very difficult to compute it from sulfur 2. But we know RAM, we can do it very well. Let's assume that this density is the right one. We plug in into the formula, and we get that with the standard assumption, we get a factor of 10 error in this assumption. Also, this is an application, apart of course, estimating metallicities and GN and so on. And this is these are my conclusions. Thank you. Beware of the TE method, which is oversimplified and maybe can get wrong metallicities. Just take into account that the TE method is based on exactly the same equation that goes into photoionization models, but in photoionization models, they are tried to be solved in a physically consistent way, and the TE method, you just make assumptions on physical properties of a medium. Thank you.
Thank you very much. So, anybody taking a debate? Yeah, it's a question.
Remarkable work. But I'm concerned about the fact that discrepancies between the TE and the photonization model. Of course, also in the photonization models, between different models, we have these 0.1 till point something dex of differences in metallicity calibration, metallicity estimations. Also, there is something that is in the direct method, we see some contamination like in the O3 that we cannot reproduce with our models. So there could be some physical processes that we haven't considered yet. So how confident we are to trust the photonization models based on all the theoretical things that we know over the direct measurements?
Okay. As I said before, the direct T method uses the same equations of the photoionization model, but it solves them by assuming constant temperature and constant density. And then, of course, you have also to consider that with the direct T method, you have to use the photoionization models to compute ionization corrections, because you don't know that. Now, I think that basically, with my experience, the fact that I am able to reproduce these many emission lines, 18 emission lines, 20 emission lines, the more the better, makes me confident that Cloudy is actually having the physics of the ionized gas right. The problem with Cloudy, the fact that until now the photoionization model has not been able to perform so well, is that you basically use a single cloud constant pressure model, which is a too simple distribution of physical properties to account from what you observe. So, of course, this has to be tested, many tests have to be done. We can compare these to ultraviolet emission lines, we can compare these to mid-infrared and far-infrared lines. So many tests has to be done, but I'm confident that maybe this could be a solution of the problem of measuring metallicity without making assumptions, relying on calibrations, and so on.
I'm very impressed about how general it is and the fact that you don't get the degenerate model. So I was wondering if we could introduce some degeneracies, if this could be introduced, for instance, in a spectral fitting code, where you could use the information that you get to inform also the star formation history determination.
You are spoiling my future project.
Okay.
But okay. Now, anyway, about the degeneracy, of course it is degenerate if you don't have enough emission lines. Because if with this model you have 2 or 3 line ratios, you can explain everything with everything, mostly. So you need really to have many emission lines with high signal to noise, and even if it's not the direct E method, aurora lines are crucial to set the physical properties of the ionized gas. So it's degenerate if you don't have enough emission lines.
But you don't get any degeneracies also from geometry, for example, from applying to galaxies where these things will be distributed in a very weird way?
No, because I don't make an assumption of geometry. What I am interested in only the distribution of the physical properties, regardless of where the gas is actually distributed. So for instance, this model works even if I have a slit and I'm taking only part of the ionized region, right? Because that changes, of course, the weights of the different contribution to the model lines.
Thank you.
Thank you. Great talk. You may have mentioned, but I may have missed this. So you have different models and then weights are assigned to different models, right? But how does that, excuse me, how does that translate to the eventual physical property, or let's say metallicity, of the H2 region that you are trying to fit to? Like, is it also a combination of those exact weights?
No, of course, I could fit models with different metallicities, but then the degeneracy, of course, would be absolute. So I do a fit with all models with the single metallicity. And a given grid for me is a grid, an ionization parameter density, and a fixed metallicity. Then from that grid, I compute the best model and the chi-square. The model with the minimum chi-square is the best model, and that gives me also the metallicity. Of course, maybe we will explore in the future what happens when combining models with two different metallicities, but I expect, and I've done some tests, that it becomes degenerate. We don't have enough constraints.
In this case, then I would change my question. Then, what is the resulting ionization parameter? Let's say it's one metallicity, sure.
Yeah.
But what's the ionization parameter? Is it the linear combination with those weights?
Yes, it's the weighted average of the ionization parameters of the clouds which contribute to the model.
Thank you.
I'll stop screaming. So let's thank Alessandro once again. And this concludes the session, and I would also like to thank all the speakers for giving really good talks. You managed to stay up with a high quality that has been throughout this conference. Been very impressed, so thank you to all the speakers and everybody asking questions. And I don't know if there is any final comments. No? Okay. You're free.